Right. This is a question that somebody's brought to my attention. It's on heterogeneous catalysis, or at least the first bit is. I think this must have come off PMT originally. And since it's a pretty weird question, I thought rather than just writing back to that one person, I'll just put a little video together for everyone's benefit. The first thing I want to say is this must be a really old question. I don't recognize it as being from one of the more recent exam papers. And some of the things it's asking about and some of the marking points are not quite what we have to look at. Nonetheless, it will use it as a good vehicle for a bit of revision on heterogeneous catalysis. The answer I've written here is as per what our exam board would ask right now. So I don't know which paper this particular question's come from. You can read the phrasing of it there. But what I would just point you in the direction of, it's on our Google Classroom, unless you're looking at this years after the event, would be the November 2021 paper one, question 4.1. That's a more recent, similar question to this. In that November 21 question that I'm referencing here, it's about heterogeneous catalysis, specifically in the Haber process. And they ask you, as part of the extended answer, it's a 6 marker, to explain how they work, basically. So the answer I've put here won't score 8 out of 8 for this particular question, but we'll use it as if it were a more modern question. And again, if you know that this came from a very recent paper, let me know, okay? Because I've got some reading to do then. But anyway, so I won't be getting 8 out of 8 for this PMT question, but I'm going to give you what we should say today, or rather, on paper one when it comes up on the 12th of June or whatever, 2023. If worst case scenario, we had a question like this. Anyway, we'll start off with a very brief bit of revision. Here's a slide from the TM work that we kind of finished on. It's on the classroom. You've got the recorded videos, the lessons there if you really need them. So in principle, then let's just remind us what we already know about catalysis. Yeah, they always provide an alternative route for the reaction to go by, which is of lower activation energy, and so they can speed up reactions. We also know already that catalysts can be reused and so forth. Homogeneous catalysis, that's where the catalyst and this reactant are in the same phase as each other. This is the other type. This is heterogeneous catalysis. Ultimately, they're surfaces on which reactions happen, basically. So the example that we've got from this transition metals lesson slide a while ago was nickel. Nickel, transition metal, obviously, acting as a surface on which the hydrogenation of an alkene can happen, and it's hydrogen and ethene in this particular case. And what we said about heterogeneous catalysis then is that on that surface, typically a transition metal or a transition metal compound, the reactants land and stick to the surface. So in this illustration here, you can see these gaseous reactants. They're supposed to be adsorbing. That's not a B, mistyped. It is adsorption. They stick to the surface. Okay, probably acting as ligands, but let's not go into that now. While adsorbed on the surface, if this thing is a good catalyst, reaction will happen basically. It might be that it weakens the bonds in the reactants that are bound to that surface and enable other things to happen. Also, the surface has got what we call active sites on it, landing zones basically, where the reactants stick. And of course, as well as having their bond strengths affected while they're on that surface, perhaps the point that the point part of the point has to be that they're being held closely together in space. So we're like forcing a collision of sorts or a proximity. Once the reactants have turned into products on the surface of this catalyst, then the idea would be that if this is a good catalyst, the reactants are held quite tightly, they adsorb well, but then the products are not held so well to the surface. And so they don't stick as well as the things that landed did, and they desorb, which is, of course, the opposite of adsorption. So basically, reactants come along, stick to the surface, undergo chemical change, and then turn into products which don't stick as well and so desorb. And of course, that then opens up the landing zone, or I should better say the active site, for another reactant to come down and land. So catalysts are reusable. So that's the principle of heterogeneous catalysis, surface on which stuff adsorbs, changes, and then desorbs. And if the reactants weren't very strongly attracted, or if the product was very strongly attracted, we wouldn't have a great catalyst because either we're not getting it to stick in the first place, or once the product formed, it's blocking the site, which doesn't mean it's reusable. So it's not really a catalyst. Okay, those are the key principles that I'll be mentioning in this answer. So I've taken this as if it were November 21's question rather than actual one that's in that paper, and done it. This would be paper one thing because it's inorganic transition metals. So how do heterogeneous catalysts work? As I just said, they provide a surface on which the reactions adsorb, undergo chemical change in the process, and then ultimately the product desorb. Now, I'm not going to mark this as per the PMT mark scheme. I'm not saying the mark scheme is wrong in any way. I'm just, as I've said, trying to make this marking it as if it were an AQA question from more recent times. So I'm not actually going to mark it per the mark scheme, but there it is in case you want to check that. You can just pause the frame if you really want to. So let's get on with this. So I'll say then, sort of O'Malley's own mark scheme here, that it's all about having a surface on which reactants can adsorb. That has to be mark worthy. Reactants can adsorb. While absorbed, they react or undergo change. Now, the mark scheme for the November question and the mark scheme for this one, whatever this has come from, does mention a few things. So we've got reactants brought together, increase the concentration because they're all on the surface together, increase the collision frequency. They're not technically colliding, they're stuck next to each other on the surface. Correctly oriented reactants on the surface. All of those things might be, what that question was looking for. But ultimately, we just keep it simple and say the reactants turn into products. All right, that's good enough. And then the idea would be that if it's a decent catalyst, those products are then not held as strongly. And so products desorbing is what I'm going to call the third mark. What's the rest of this question want from us? Give one example of a reaction catalyzed in this way. We've got several. So you've just seen the nickel hydrogenation example. Here are a few others that you should be reminded of. The idea that iron can be used to catalyze the Haber process reaction. That's a good one. V2O5 can be used to catalyze the oxidation of SO2 to SO3. Whether you call it reversible or not is besides the point. It is reversible. Palladium or rhodium or some other metals, possibly platinum, in catalytic converters of cars. Now, I don't know whether I should tick that because obviously I'm going off piste a bit with the mark scheme here, but I'd suggest that if I had to write this, I'd probably want to give an equation for it. And we're going outside of what's officially on the spec here, but the way that what the catalytic converters do, they take like harmful products from combustion of fuel and turn them into less harmful products. So you could assume that there's some NO2 or some NO, just a nitrogen oxide, something that causes acid rain. Think back to GCSE, coming off the exhaust fumes of this engine. And if we just turn that into something less harmful, such as nitrogen and oxygen, then that would be a sensible assumption about the sort of reactions that are going on in catalytic converters. I just need to balance that then. And that'd be a suitable one, but maybe the Haber process one's a better choice because it's so obvious and well known. So I've probably got one mark for that. I'm trying to second guess how I can get two more marks out of this, and this is probably where it breaks down a bit. Explain why the catalysts have different activities. Now, this really isn't on our spec per se. I suppose we could be expected to assume a few things though, so maybe it could be on our spec in a roundabout way. This is a bit to do with the strength of the adsorption and the strength of the desorption. And what makes it, as I said, a good catalyst would be one that holds the reactants tightly. So has a strong adsorption strength, whatever we would call that, like gets them to stick well, and also a very weak attraction to the products. And so they desorb. Again, as I've said, re-enabling the active site, like as in making it available again for something else. So that's where this final statement comes in, sort of. So then the surface of the metal is available for more reactants to adsorb. I haven't really gone into much detail there. I have gone fully off piste on this mark scheme now, but I'd just say really had to, and this would be a real stretch. We'd need to probably think about the strength of the adsorption for the reactants being a good thing, and also hopefully a weak strength for the absorption of the products. So what do I want to say here? A weak desorption. I'll probably not phrase that very well. I'm going to scratch that. I'm just going to say the idea that the products aren't held as tightly and so leave. So the best catalysts adsorb well and desorb well as well because they don't attract the products. I'm just going to shut the door. It's getting noisy, and then I'm going to look at part two of this question. Here we go. So there it is. And I think you'd be better off looking at November 21, paper one, question 4.1 for a bit of heterogeneous catalysis, long answer, than this question if you've come across it. Now, on to the second part of this problem, which is also a pretty bad one, to be honest. I'm only going to give you an outline here. Again, if you've accessed this question yourselves, you've got the mark scheme. Just in case you haven't, you can always just freeze frame on that if you really want it. This is a horrific question, I've got to be honest. And again, what I think it's old is it's out of 7, and that one was out of 8. That's a bit unusual, to be honest, for a single part of the problem. I'm only going to give you the outline here. This is like a sort of nightmare scenario on a redox titration type problem. And I'll say it's a nightmare scenario because it's complicated. This is one that really thinking outside the box to a limit. This is like a hard chem sheets problem that takes you miles outside of a typical exam question. Again, despite me saying that, please don't switch off. Just give this 10 minutes at most because it will give you some food for thought. And this is a could be a question that we get. If so, it'd be horrific. I've got the examiner's report. I'll have a quick look at in the end. So I'm not going to write a full answer. I'm not going to get 7 out of 7. I'm just trying to give you the principles here so you can see how you might approach such a convoluted problem. Basically, we're told we've got a solution. I'm just going to take a bit of scrap paper as well, which contains iron 3 and iron 2. Now, we're not doing electrochemical cells here, but that's the sort of thing we might have drawn a salt bridge coming out of and platinum, but wrong topic. They're also paper 1 in organic stroke physical. We're told that we've got zinc present as well, and we're pointing without e-values. We've still had it told to us. We could have worked it out with e-values that zinc can reduce iron 3. The question wants us to suggest how we would go about quantifying how much iron 2. I'm just trying to actually read the question while talking about it. Yeah, determine the percentage of iron present as iron 3, in a solution that contains iron 3 and iron 2. So in other words, we've got this mixture of iron 3 and iron 2, and we want to find out just how much iron 3 is in there. So basically, the way we do this is somehow find out how much iron 2 is in there, and then maybe we can find out how much iron 2 and iron 3 is in there, and then we could look at the difference between those two and say, well, how much iron 3 is there then? That's where we're going with this. But as I say, it's quite convoluted. I think it is worth a listen, even though I'm kind of trying to discredit this question as not like, if it come up, would want to be doing well at it. The fact that we're told the zinc can reduce 3 is a major tip here. So maybe we can do something to quantify how much iron 2 there is, and then maybe we can turn all the iron 3 into iron 2 and do it again. And then the difference will be how much iron 3 there was, which has now been turned into iron 2. So let's first of all quantify. I'm going to move on to this thing now. Let's first of all find out how much iron 2 there is. So quantify the iron 2. And I know the question is asking for iron 3, but I won't lose sight of that. There's absolutely, there's limited mention of a redox titration here. We've just been told we've got a solution of potassium dichromate. And again, we should just know that potassium dichromate is a good oxidizing agent. E-values would help us with this, but I'll tell you then that if we react the dichromate, 2 minus even, gosh, with H plus, if we put that with this solution, then the iron 2 will be oxidized up to iron 3. Now, clearly, this is not a balanced ionic equation there. I will quickly write the half equations. So we've got dichromate in the presence of H plus getting reduced to chromium 3 plus, which is going to be irrelevant in this really, and some water molecules. And the point is that that reduction of dichromate will happen when we put the dichromate with something it can oxidize. And the iron 2 in all of this can be oxidized up to iron 3. And there's a bit of balancing to do there, which I'm not going to do because, as I said, I'm giving you the outline. But there's basically a 6-to-1 ratio of iron 2 to dichromate in this reaction. So what we're saying is that if we take a given, I hate this question, but I think it's worth you hearing it. Hopefully it helps somewhat. Of this iron 2 stroke iron 3 solution, we take a known volume of it, and if we titrate that against the dichromate solution, which is going to have to be acidified, then we can find out how many CM's cubes, and knowing the concentration, how many moles of dichromate have to be added to, I was about to say neutralize then, it's redox, to fully oxidize all the iron 2. And we might even have to talk about the end point. Now, we've looked at redox titrations. The example we used was manganate. Have a look at the transition metals video notes to remind yourself of that possibly. But here, the dichromate would be going from orange to green, and eventually it would stop going green. And then, well, I'm not going to say more than that now. This is a bit outside of our spec. If manganate was the question, that'd be better. Anyway, if we titrate our iron 2, iron 3 mixture against dichromate and do it well, with known volumes of both and the known concentration of the dichromate, then we can basically find out how many mole of iron 2 there were initially in that mixture of iron 2 and iron 3. And for now, I'm just going to call that mole A. Okay. Then what I can do is take another known quantity of this iron 2, iron 3 mixture that we're told about in the question and reduce all the iron 3 in the mixture. We need to know what volume of mixture we've got there with zinc. So what I've done here, I've worked out how many moles of iron 2 were already in the mixture, and now I'm going to take all the iron 3 and turn that into iron 2 as well, by reduction with zinc. Again, just a couple of half equations for you. The zinc would be oxidized up to zinc 2+. That's like a general bit of knowledge that we should be aware of. It's the only zinc ion we've ever met, zinc 2+. Again, the iron 3 this time gets reduced. There's a 2-to-1 ratio. Can you see that? I'm not combining it for this outline video, but the electrons there would be like 2 iron 3s for every zinc. We don't need to know really how much zinc as long as there's an excess of it. Now, again, I had a quick cheeky peep at the mark scheme. I can see they talk about filtering out the zinc. It's in the examiner's report, I think, but I'll come back to that in a minute. So if we did this, what we'll have had to do is take a known volume of this iron 2 stroke iron 3 mixture. We'll have added in a bunch of zinc, and we'll have basically taken all the iron 3 out of that by converting it into iron 2. So there's now a lot more iron 2 in this beaker than there was in the original mixture because all the iron 3 has been converted. Then, because we'd have used an excess of zinc, we'd have to filter that out, which according to the examiner's report is something that basically nobody mentioned. But then we could do a second redox titration where we put this new iron 2 solution where all the iron 3 has been converted. Again, do a redox titration against the dichromate that we're told about in the question. And it would have to be acidified dichromate. It says with sulfuric acid there, so that's kind of covered for us. When we do that, again, you'll find out the moles of dichromate reacting through the fact that you've got it's tighter and what concentration it is to begin with. And therefore, you can deduce the moles of iron 2 in this new solution. And I'll let that number of moles of iron 2 be B. Therefore, because it's 1-to-1 between iron 3 and iron 2, the moles of iron 3, which is what the question's asking us for here, in that original mixture is basically how much iron 2 there was in the second titration, which is when all the iron 3 and the pre-existing iron 2 got reacted with dichromate. Subtract how much of that iron 2 from the second titration was already iron 2 as determined by the first titration. But yeah, there it is. And so the difference basically. It's weird that you get a 7 marker here. That's what makes me think this question is old or from a slightly different spec to us. But definitely it is on a theme. This is really a sort of E-cell question without any E values in that we've been given reducing and oxidizing power. It's sort of got year 12 redox running through it because, well, it's redox. It's got half equations that I haven't put together to get you 6-to-1 and your whatever to 1 ratio. And also it's redox titrations, which is filed under transition metals. Plus it's practical, though this is not one of the required practicals. It's titrations, which are and redox or acid-base titrations. So a really tricky question, but there it is. To finish now, there's the mark scheme in case you haven't found this on PMT, wherever else you might look in case you want to do it legitimately and mark your own. But also just a quick look at the examiner's report for whenever this problem was set. So for part A, which was the bit about the heterogeneous catalysis, most candidates gave a good explanation, high marks were scored. Yeah, interesting. Um, by contrast, very few or few gave a good outline plan here. I'm only going to paraphrase it for you, but you can always pause it and read it if you think it's really worth it. But basically saying that students got into a right muddle with just knowing what to do next, not being specific about the fact that if you're going to do titrations, you have to know what volumes are going in. It's typically 25 of something pipetted into a flask and whatever the burette titer is, isn't it? But stating what the volumes are. And here you can see, although most use the fact that zinc can reduce iron 3 to iron 2, very few stated that the zinc would have to be removed. Zinc's a solid, isn't it? So if you're going to chuck a load of zinc in to turn on iron 3 into iron 2, you're going to want to filter it afterward. Actually, to truly finish on this, part of the reason why you'd have to filter it rather than just leave it in is because, again, without E values, it's almost impossible to see. Zinc can be oxidized. We saw it going up to zinc 2. And if it can be oxidized by like iron 3, when it reduces iron 3 down to iron 2, it will definitely get oxidized by a better oxidizing agent like dichromate. So if we did the titration with the zinc left in, it'd oxidize the dichromate, be oxidized by the dichromate. I'm not sure how much of those finer points are really necessary, but hopefully it's just giving you a chance to think about how you could put something like this together in a real, I'd say, worst case scenario. To be honest. Anyway, there it is. Hope